Good morning, everybody. Welcome to today's webinar. We're looking at modelling the coronavirus pandemic with Simon Roberts. I'm going to be your host. Sarah's the man. I'll introduce Simon in a moment. I'm the Community Outreach Manager for the North East and for Yorkshire and Cumbria. I oversee all the communities and the community leaders in that area. This webinar is part of the CAS Virtual Showcase, which is a 2-week window of webinars designed to support the CAS community. During this session, please use the question window on the right-hand side of your screen to ask questions rather than the chat. If it's a question that I need to ask Simon mid-presentation, then I'll just stop him and ask the question, but otherwise we'll have questions at the end as well. All attendees will be in listen-only mode. The top of the window has an orange rectangle which can be expanded or collapsed. If you're using social media, the hashtag for this event is hashtag CAS Virtual 20. I'll hand over to Simon now. Thank you.
Thank you very much, Sarah. So the title for today is Modelling the Coronavirus Pandemic, and I've got to say right from the start that I'm not an expert. I had this idea and I thought it'd be nice as a problem-solving exercise. You know, how is it possible to show this in a way that might be engaging? I certainly didn't want to go down the lines of just doing it in Python, just doing it mathematically. I wanted something visual, and the fallback was Scratch because it is visual. It does do something that that Python doesn't do. Python, I suppose I could have used Pygame maybe, but that involves learning that library of tools. And doing this in Scratch means that it's suitable for a wide range of people learning computing. And that's really what it's about. It's about computing. It's taking those ideas that we learn in computing and putting it into a context that right now everybody knows about. I've got to admit also I'm quite wary about this idea of modelling something that is so prevalent at the minute, and there have been an awful lot of losses, an awful lot of deaths, and I'm concerned, but that doesn't stop me also wanting to model this in a way that promotes understanding of how diseases are transmitted. It could be influenza, it could be a particular disease. So anyway, going to get started. Let's have a look at the aims and the objectives. And first of all, what we're looking at, sorry, just making sure that you can see what I can see.
All fine, Simon, we can see, yeah.
Yeah, that's okay. So basically the aims and the objectives, we're going to go through those. What was I hoping to achieve? I've gone through some of those, but I will go through them again. Then looking at two really key important computational thinking ideas, decomposition and abstraction. How do those affect what we're going to do with this particular model, with this particular problem to solve? And then obviously there's using Scratch. We're going to use some of the PRIM model, the PRIM methodology, this idea of looking at code that's already there and then taking it and modifying it, making it. Developing the model and looking at how else we can develop that, and then evaluating, thinking, how have I done this? And, possibly if I was to do it again in the future, what would I do differently? So really, by the time we get to the end of the workshop, I want you to have thought about those and feel confident enough to be able to think, well, actually, yeah, we can take on an idea no matter what it is. Just as an aside, the other idea that I was thinking about right at the start of this, I was thinking about this back at the start of the current restrictions. I was thinking that maybe I'd do some sort of app using the microbits, again, sort of aimed at Key Stage 3, and I didn't do it. Maybe I could have done, but it's follows the same kind of lines. It follows the same kind of idea of problem solving in terms of what do you want to do, and then going through a process of being able to do that. So, aims and objectives. So what I wanted to do right at the start is I wanted to see that it's possible to create a model that mimics real life. It's part of the Key Stage 3 computing curriculum. It's part of what we use computers for. We want to be able to build that model using software, and in this case I've chosen Scratch. I've looked slightly at some other piece of software. I'm looking at Python using Pygame, but Scratch is the one that I've gone for. And finally, to understand that models have their limits, and we'll really be looking at that in the evaluation as well. First of all, decomposition. Modeling disease transmission. Now, the spider diagram is going to come up in a second, and I just want to give you some time to think about what kind of things you could think about when you're wanting to model the disease being transmitted from one person to another, and then looking at maybe how that affects an entire population. So this is what I was thinking of, and it may be that what you're thinking of is on there, or it may be that you have other things that you would put on. But there we have them. That's what I was thinking at the time. Now, some of these are just things that affect our current situation, but there are other things that don't. So, for example, movement, people going from one place to another. And don't forget that when you touch something, when you go very close to somebody else, then it's possible that you could pass the disease on to somebody else. Possible. Okay. There's the idea of being infected and the course of the disease, you know, picking up the virus, becoming infected, becoming ill, which is the next one. The end of the disease. Now, we hope that the vast majority of people will have the disease in quite a mild form and they will recover. But as we also know, with any disease, there's a possibility that people can die. So that's, again, another outcome of the disease. We're also hopeful that immunity can be part of this disease. So once people have had the disease and they can become immune. Social distancing is a term that's been used an awful lot. How do we keep apart from each other socially? So there's the 2 meter social distancing rule, and recently they're talking about reducing it to 1 meter in certain circumstances. Across the world, there are different social distancing measures, you know, whether it's 1.5 meters, 1.8 meters, and so on. Self-isolation. This is this term where if you are infected, if you are ill, then you isolate yourself from other people. So for 14 days or 7 days if you've had the disease or so on. Quarantine is even if you don't know whether you've had the disease, then you are put into a place. So to just prevent other people from getting that disease. Bubbles, that's been talked about as well recently. You know, you can form a bubble with another household, or somebody can join your bubble, and it's even been talked about in schools, so that when pupils are in schools, they have a bubble, and if somebody in that bubble is infected, then, you know, then all of the bubble would need to go into self-isolation. But this idea that, you know, you have people in one particular area or one set of contacts that are going to minimize the contact with people outside of that bubble. So there are many different things that we can think about. In reality, though, what we want to do is we want to focus on what is important. And that is where abstraction comes in. Abstraction is the reduction of unnecessary complexity. So basically focus on what's important, we forget about the rest. So in this case, in this model, what we really want to do is we want to focus on movement, getting people around, okay? We're going to treat this as though it's a normal situation, and people do move around. Once they move around, they might bump into people, they might pick up the disease. So we need to think about the course of the disease, you know, the getting infected, the recovery, the end of the disease. And another thing that would be quite nice is, you know, we've been talking a lot about numbers. You've seen a lot about numbers in the media, and it might be nice to get some sort of counting up done. Now, obviously, we're going to be dealing with a far smaller set of numbers, but we might extrapolate that later on when we start talking in the evaluation. But those are really the things that I wanted to focus on in this model. So the idea of the bubbles, the idea of self-isolation or the quarantining hasn't really been taken into account. We can abstract that away, and it may be something that gets developed in a future version of this model. We're also going to make that assumption that all of this is factual, and it might well not be, okay? We've got to remember that, you know, if our model is taking everything as fact, then it will work in that particular way. But if you insert errors into your model, then those errors will come out as problems in the future. So there is that assumption, but that doesn't necessarily mean that that assumption is always true. And we, again, need to think about that when we're looking at our model in the evaluation. There are other models out there, you know, the models that have been created by Imperial College in London, the models that have been created by the SAGE group, the people that advise the government. There will be models that that have got a wider remit, and they will take far more variables and factors into their model. But in this case, this is what we're going to work with. So this is what I'm sort of looking like. This is what I was hoping to have. And these are screenshots of my thoughts. So we would have some sort of circle that represents a person, and those circles would move around the screen. There would be some boxes that represent the numbers, and the different colours represent different things. So what we have got is we have got blue, which represents a healthy person walking around. The light blue represents a healthy person. The purple represents an infected person. A red person is ill, okay? And at the time that they're ill, they do nothing. And I think, you know, the idea with the movement is that when they become ill, they stop. When they're normal, they walk around. When they are infected, they walk around. When they're ill, they stop. And then after the illness, they might become immune. That's the green one. And then they'll carry on walking around again, just like normal. So this is what we have got. This is what the aim is. And I'm going to show you a video of it, and then we're going to look at the code. So we're going a little bit backwards. However, this is the video. So they're all healthy at a minute, and then one gets ill, the disease gets passed around, and when they become ill, they stop, and then they will carry on. And lots of people are ill, and then after they're ill, then they carry on as before. And in this particular case, we can see the numbers at the end. There's, don't quite know, there's an error in here somewhere, a bug in here somewhere, so the debugging is something that will have to happen on this. We've got a minus number, which isn't right. There should be 25 people in there, and we've got 24 that are immune. One person's dead, unfortunately. One person is still seen as being healthy, and obviously there is a bug somewhere. And again, debugging is part of our computational thinking. It's something we need to work our way through. This is the first part of the code. Now, the link here is a link to Scratch, and you're welcome to have a look inside, and you can actually just have a go at this. But what I want to do here is I want to talk through some aspects of the code. I want to talk through some aspects of the structures that we need to look at, some things that the pupils will have learned about, and this is just putting it into context. And the first thing that we can look at is a sequence, putting things in order, okay? So we can see here that we have got things happening in an order. We've got some variables being set, switching costumes, waiting, switching costumes, and all of these are in a particular order, okay? Every one of these scripts has got something in a particular order in order to do the job that it needs to do. The other main structure, or one of the other main structures, is selection, okay? So selection is about decision making, and here we have got an if, and this is the only if that we've got here. If color black is touching purple, so if we have got this sprite and the border of it is touching purple, so that means if it's not just slightly touching, but if it's made a definite contact, if it's touching purple, if it's touching somebody that is infected, or is touching somebody that is ill, which is the red color, and current status is healthy. So there's a bit of Boolean logic in there as well for the key stage 3, but we can equally say this as a statement. If you are touching something that's purple, if you're touching somebody that is ill, sorry, if you're touching somebody that is infected or touching somebody that is ill and your current status is healthy, then, well, you're going to have some changes. You are going to be incubating, okay? You are going to be infected. Ill time is set to 0. Don't believe that variable means anything in this particular code. Again, something to evaluate away. This ill time is picking a random between 2 and 14 days. Those are the days that we've been told by the media, by the news, by the government. You know, you may be potentially infected for up to 14 days. There are some cases it might even have been longer than that. But, you know, you may be ill for 2 to 14 days. Switch costume to incubating. No, you're infected. You're incubating that virus. Set current status to incubating. Okay, that's actually happened twice there. Again, little bug that needs to be fixed. Wait this ill time. Well, you're going to wait a certain number of seconds. You're still going to be moving around, okay, but you are going to be walking around for between 2 and 14 seconds. Okay, that's just that variable that's been set there. Switch costume to ill. So after you've been incubating, you are then ill. Set current status to ill, and you are going to be ill for between 3 and 6 days, or 3 and 6 seconds. And again, you know, that's what some people have said, that that is a reasonable amount. I mean, that might be worth changing. It may be that if more data comes out that people are regularly ill for less or more time than that, but there has been news that some people have been ill for far longer. Once that has happened, though, you then switch costume to immune, and then set current status to immune and carry on as before. Okay, because this is in a forever loop. So it's just going to keep on doing that forever. Okay. This script here, when the green flag is clicked, switch costume to healthy. This is really for the starting point. So at the start, everybody's healthy, set the current status to healthy, point in direction, and this is just some movement. Okay. So point in direction somewhere between 1 degree and 359 degrees at a point in a random direction, and you move. If you're on edge, bounce. So this script here, reading it through, is all about just moving, okay? And nobody moves faster, nobody moves slower, they're all moving at one step. When this sprite is clicked, okay, so this is how you get somebody infected, okay? If you want to get somebody infected, you have to click on them, okay? Set current status to incubating, and so on. So there are 2 sprites here. This one is for all of the sprites generally, and this one is so that if you do click on that sprite, then you can start the process. You can create your patient 0. Again, it's the same set of code here as it is down here, except we've got a different starting condition. Here is if you are touching somebody that is incubating, you know, infected, or somebody that is ill and your status is healthy. But here, this is where you get clicked on. This is for your patient 0. That was version 1-ish. You know, there's bugs, there's errors in it, and I've pointed those out, and that's fine. And it's something to work on. It's something to make sure that we do try to reduce. Please put any questions in the questions box. This one here went through several different versions, and we have got some more blocks. Okay, so really what we've got here is we have got, well, let's go through this one. So we've got a forever block, and we've got an if. If current status is ill, then wait, pick random 3 to 6. So this is the amount of days that are going to be ill, the amount of hours that are going to be ill. And then if pick random between pick 1 to 100, if that is greater than 98. So if it's 99 or 100, then you are going to hide. And then this one here will die. Okay, so change the dead number by 1, change the ill number by -1, and so on. Okay, stop the scripts in this sprite, stop this script. So it means that if any of the other sprites were working, then this one would stop the other scripts in this sprite, and then it would stop this script. Else, switch costume to immune. So if this random number was between 1 and 98, then we'd be immune. Okay, the current status will be set to immune. You change the immune number by 1 and the ill number by -1. So this script here is all about the end of the disease. This one
Simon,
here.
can I just ask you a
Hello.
question?
Yeah.
Somebody says, how does a sprite die?
How does a sprite? It's a representation. The sprite doesn't die, but what you will do is you'll stop the scripts in that sprite and you'll hide that sprite. So the sprite doesn't die, but you stop it working, and all the other sprites in the model will carry on. I hope that answers your question. It's just you can hide and you can stop that script from having. You stop that script from running and stop all the other scripts in the sprite from running.
That's great, thank you. The other one was, just before you carry on, would you get the pupils to recreate this, or would you give them some code to debug?
I think I would do a bit of everything. I think, you could do some design work. You could do the decomposition of the abstraction. I think doing this bit of coding did take a bit of time. So it depended what your outcome was wanting, or what you wanted your outcome to be. If it was understanding the code, then you deal with it as a predict activity. So you take your prim methodology and you do some prediction and reading that code and understanding what that code does. Alternatively, you could say, right, there you go, I want you to modify that and I want you to improve it. I want you to understand what's going on so that you can modify it and improve it. It depends which stage your pupils are at. So the idea with the pupils would be you can use this activity in many different ways, and all the time they're trying to understand a little bit more about the way that the disease is spread. Is that okay, Sarah?
That's fine. Can I ask one more question? So somebody's asked, so if the random number is greater than 98, then is the sprite declared dead?
Yeah. So this is one of those things where what's the likelihood of the sprite dying if it gets the disease? So if it gets the disease, what we're saying here, we're making this assumption, rightly or wrongly, that there's a 2% chance of death if you get the disease. Now, I don't know whether that's right or wrong, and I would hope that somebody would be able to correct that or change that. But all that you would do, if you wanted to change this, you'd pick your random number between 1 and 100, and then you could change your 98 to 99, or you could change your 1 to 1000 and it needs to be greater than 998, depending on what your ratio of becoming immune or dying would be. And obviously we've seen in the news that there are different death rates for different age groups, and that's another complexity that we haven't considered here and we're not going to. So this random number, this is one of the things that could be changed as part of the model to make it more accurate, to make it a better model. This is something that people at Imperial or Sage would be doing to make their model as accurate as it can be. Is that okay?
Yeah, thank you.
Okay. This one here, wait a second. I think I put that wait a second in just to make sure that it happened after everything else was sorted. So we click on the green flag, wait a second to make sure everything's calmed down with other things that are happening, and then change healthy number by 1, and then go to a random place. Okay, switch costume to healthy, set current status to healthy, point in direction 1 to 359. So this is the starting point. You'll go into a random place, you're pointing in a random direction. And then this one here, I believe, is to do with movement. Okay, oh no, these other ones are to do with movement as well. They're all based around pace. So this variable pace is the movement of steps, and basically we can have movement on all of these. I think this one might be, no, if this one's immune, so if current status is immune, then move pace number of steps, and if on edge bounce. If you're incubating, move pace number of steps if on edge bounce. This one here, forever. If you're healthy, then move pace number of steps. However, a nested if. So this is another structure, an if within an if, a nested if. Same thing's happening here. So if you're healthy, and if you are touching color red or touching color purple, and your current status is healthy, then set your current status to incubating, and this is similar to what we saw before in that V1. Okay, switch costume to incubating. And then that would trigger this one, which is just continue moving if you're incubating. Okay. If you are incubating, then this one here is going to be triggered. So if the current status is the same as incubating, if you're infected, then pick your random number of days between 2 and 14, and after that you are then going to be ill, and then if you are ill, then this one will come into place. So we're starting to separate up each of our scripts into smaller problems. So this again is part of our decomposition. We're starting to create our sub procedures that do a smaller job. All of the time they're pretty much when the green flag is clicked, and the only one that is not on a green flag being clicked is when this sprite is clicked. When this sprite is clicked, then you can become infected. You're incubating the disease. Switch costume to incubating and then change the numbers. So that's an overview, a prediction of what we have seen. And if we look back to our previous slide, let's just go back to here. There we go. And if we run that through, we can see that in practice again. And I would encourage you to have a look at it on Scratch, because you can go through as many times and it will always look different. Because you've got that random element of where these things are going, where they're going to be. What we really want to see is that, first of all, that we can model something. And, you know, I know that there are weaknesses with this, and we'd acknowledge that with any piece of work that we do in school. You know, it's not going to be as perfect as we want it to be. But what we can do, once we've got a basic model set up, we can then start changing the variables and seeing what effect it has on the outcomes. And ultimately, that's what modeling is. And it doesn't matter whether you're modeling a tuckshop spreadsheet or whether you're doing some sort of modeling in Scratch. What we can do, and these are quite nice things to change, we could change the speed. You know, does it make a difference if the models are moving faster? Does it make a difference if the models are moving slower? Does it make a difference if we change the number of sprites? Obviously, if we have the number of sprites larger, then that means they're going to be closer together. They're more likely to hit into each other. And we can also change the number of sprites smaller, which means that they're further apart. They're less likely to hit into each other, less likely to pass the disease on. We could do the same with making the sprites larger or smaller. And again, that would affect the amount of times they might touch each other or pass by each other. In each case, we can make predictions, we can run, we can investigate, we can modify the code, or we can make new pieces of code that do different things. And I think the idea with the computer model is that we can do that in a way that we can't do with many other in many other ways. We can have a model running through 100 times or 1,000 times, and we can see what the outcomes might be. And that is really the point. Once you've got a model, then you can take your understanding of that model and change things and see if it makes a difference. Developing the models further. Now, I think it was Imperial that produced some models, some bouncing ball models in a similar way, and they went one stage further, where they would have, or several stages further, where they demonstrated what self-isolation would be like. So if you're infected, then stop moving and prevent others from coming near. So it's possible that you could have like boxes drawn around the infected sprite. So if that box gets drawn around you, then the other sprites will bounce away. It's increasing that distance between the infected sprite and something else. Quarantining. If moving from a different place, don't move, don't encounter others. And I suppose that's what they did right at the start. Back in March, they had a flight of people coming in from China, and they looked into a quarantine hotel, I believe somewhere near Merseyside. And the same kind of thing is happening in New Zealand and Australia, where people that are coming into those countries, they are placed into quarantine. They're placed into a place where they're not going to have contact with other people. How would we model that? Well, I suppose what we could do is, if they're infected, then they stay still and don't touch anybody else, or go to a place. You move them into a square on the screen that might have that might be the equivalent of the quarantine hotel. So it would be an X and a Y position. So you move there, and then after a certain time, then they move back out and they can carry on moving. But hopefully by that time, they will either be immune or they will still be healthy. Social and physical distancing. I wasn't sure how to do this one. Change the movement algorithm to prevent touching or close contact. So there would have to be some sort of way of identifying how close one sprite was to another sprite. If there is an X value on that sprite and a Y value on that sprite, then it's possible that you could compare that sprite to the other sprites that are around and don't go close, maybe. It's not something that I did develop here, but it's something that possibly could be one that is very important right now. This social or physical distancing is something that is being looked at now by the government, in terms of reducing our social distancing in the UK from 2 meters to maybe less than 2 meters in certain circumstances. So trying to model that and seeing what the difference would be. How good is the model? Well, it is what it is. It's a model that's been made in scratch, and I think it's far more important that this model has been used to understand computational thinking rather than it being an accurate model of the coronavirus pandemic. I think if we consider that we have got 25 sprites on the screen and we've got 70 odd million people in the UK, each of those sprites is probably about 2.5 or 3 million people. And in terms of the accuracy, so far in the UK, we've got over 40,000 people that have died. But if one sprite dies in this model, then that represents 3.5 million people, and that's not accurate. But again, I don't think that's the point. In this particular case, it's about doing the decomposition and the abstraction and building the model, and then evaluating it afterwards, seeing how you can potentially improve it, or how you can change the model and see what you can do to model it better. How does it compare to the models used by Imperial College, the World Health Organization, SAGE? Well, I don't think it is comparable. But again, I don't think that's the point. I think we've got some pupils that will appreciate the idea that this is a model, and they will then have an understanding about what those Imperial College models or the WHO models will do. The third point here, I think, is the most important thing. Helping our understanding of computing and programming. That's what we need to do. We need to be able, in Key Stage 3, to be able to model these real-life scenarios. But also we've got that secondary outcome where we might have a better understanding of science, or we might have a better understanding of disease and how diseases are caused. It may be that we can build our model in the future to maybe click on a sprite with a vaccine. That'll be something that may be a lovely development in this model. But that, I believe, is the end of the workshop, the end of the presentation. Thank you for paying attention. Thank you for listening. If you've got any questions, I'll happily answer them. And yeah, thank you very much.
Thanks, Simon, for that. I think we've answered all the questions. from what I can see there. So thank you, that was really interesting. Thanks everyone for joining us today, and thanks for Simon for presenting. Lots of highlights for me in that I find it really interesting that the fact that it was so topical for children. I just, there's so much going on there, so much that you can use in class for children to think about. And I'm really for having the code out there and then children unpicking it. Loads to take in, so thank you for that. And I did like the way at the end that you talked about evaluating it. I think sometimes we forget to evaluate what we've done in computing and in lots of different curriculum areas, so thank you, it was just brilliant.
You're very welcome.
Highlights? That's fine. Any highlights that everyone who's been in the session today, it would be great if you could share yours on social media, on the CAS website, and also in our CAS Facebook groups, where I'm sure Simon could catch up on any questions afterwards. Oh, thank you for that. Oh, brilliant. And also on Simon's Facebook page for the Computing Hub, for Carmel Computing Hub. So thank you. At the end of this webinar, a short survey will appear on the screen. We'd be grateful if you could take a minute to complete the survey. Additionally, in about a week's time, you'll receive an email with a CPD certificate confirming your attendance at this session. A recording, because I know some of you have asked about this, a recording of this webinar will be available on the CAS website in the near future. We do hope to see you at other sessions in the showcase, so please do continue to spread the word with that hashtag on Twitter about the first ever CAS Virtual Showcase. Thank you for joining, and we'll hope to see you next time. And thanks again, Simon. Brilliant.
Thank you, Sarah. Thanks for inviting me.
Thank you.